interlaced, and there's so much to do with this stuff. We got to keep going. Okay. Okay, so dynamically, let's think about this. And you know how much I love these Fermi type problems. Right? This is good for thinking. Yeah. Maybe it's just fun for me. I don't know. How much energy was that? Oh, did we come up with about 600,000 joules, give or take? 700,000? I know I could be off by several tenths of it, or several thousand.
What are we talking about? On that
The total energy that was absorbed.
The Q net?
Yeah.
652,000.
Oh, wow. Okay, I do closer than I thought I was going to be. Oh, yay, me. Doesn't happen very often. My estimates used to be rock solid. And this year, especially this quarter, they just got a hell in a handbasket. I don't know why. My daughter said, "You're getting old, Dad." I don't know. Okay, so now let's modify this and see what it might really be. Okay. So, what's really going on here? What's the big thing that's happening? If I were to draw this picture after the fact, okay, it's lifted up this distance. What does this sketch look like? Put this guy in place. The water level, I know this wasn't very good to scale, but I'll use about the same. It was about here before, right? Now it's going to be somehow lower. Even with thermal expansion, which is not that much thermal expansion because it's not a huge temperature rise. And if this was 3, 5 is somewhere up here. So now this thing is somewhere up here. Reasonable?
The water's lower.
Water's a little bit lower. If this was L naught, now it's dropped a little bit. And the amount of that drop is due to all of these water particles in here.
Oh, yeah, because
Evaporated. Now it's expanded. There's the expansion you were talking about. We were talking about phase change on Tuesday. You said, oh, but isn't it going to change the volume? Absolutely.
Yeah.
Didn't want to worry about it too much at that point, but you betcha. Okay, so now we got this. So what can we say then? Without knowing everything else now, we got some few modifications to make here. Without knowing everything, let's estimate what is the pressure inside here. And by the way, from here to here now is 0.05 meters. This distance originally was 0.03. Not anymore, because it's dropped, but it was about that. Fair enough? So let's figure out what is the pressure of the gas. We're going to do all kinds of stuff with this in the next few minutes. Quick answer, doesn't change. This is a frictionless system, which means as this heats up and you build up more and more gas in here, the piston's going to rise to keep the balance of force pushing up equal to the force pushing down. Right? If you're not in balance, it's going to pop off or it's going to drop. So it's going to rise and maintain equilibrium. Which means that P gas is still going to be equal to P atmosphere plus the mass of the cap times G divided by the area of the cap. So we can calculate that number. It's going to be, give or take, this number's tiny. I estimated it, but it's going to be about 1.013 or something. So we're only talking about a 0.3% change in pressure when you have this cap on there. Atmospheric pressure is huge by comparison to most things. So this is about 0.013. That 3 is probably not even going to matter in our final calculation, but it's pretty close to atmosphere still. So we got 10 to the 5th newtons per meter squared. Reasonable? I'll draw a quick picture. So you've got P atmosphere, and then you've got mg. Pressure of the gas, and And the associated force has to push back against those two. Okay? That's the key. Now, figure out some things. Let's make some better estimates here. Okay? To begin with, how much water is now in gas form? Okay? We need to know this in order to calculate the heat associated with phase change. We can't do it without it. Fair enough? We have to introduce a concept some of you may know of, some of you may not have heard of it. It's called the ideal gas law. First order approximation to the interaction between interacting gas particles in a closed system. Only requirement is that we're at relatively low density and relatively high temperatures. Everything starts sticking a little bit when you start getting colder and you start packing things into more closer and closer spaces. So we will start by introducing the ideal gas law. And what we have here is the relationship between the pressure of a gas, the volume of a gas, the numerical quantity of a gas, and the temperature of the gas in Kelvin. Okay? This is a weird, important state relationship that relates all of these physical quantities together, observable physical quantities, well, maybe with the exception of N. It turns out, if you take the product of the pressure of a gas and the volume of a gas, and divide it by physically the numerical quantity of a gas, 150 gas particles, not moles, just 150 particles. And you multiply that by the temperature of the gas in Kelvin, this number always equals one value. And we've already seen that value before, but we didn't necessarily assign all of its importance. It always equals the Boltzmann constant. You may have seen it in its molar form, but we're going to use it in its very physical Boltzmann constant form. Okay? This is 1.38 times 10 to the negative 23rd joules per Kelvin. Now, in order to know how much energy was involved in the phase change, I got to know how much water underwent that phase change. So I need N gas. Here's why. The amount of mass that underwent phase change. Now I assume 15%, but the actual amount that underwent phase change is going to be equal to the number of gas particles that underwent that phase change times the average mass of one particle. So the average mass of a single gas particle. Now I will make an estimate here to maybe help your sensibilities. M gas, what was M gas for water? Do you remember? Or for, not for water, for air?
2 point something. Right?
It's about 4.7 times 10 to the negative 26. Okay, that's the average mass of a gas particle. That's 2 oxygens, approximately 2 nitrogens. Water is about half that. A little more than half that. So half of 4.7 is about 2.4. So the average mass of water, a single molecule of water, is give or take 2.4 times 10 to the negative 26th. Now, if that is disturbing to you, then you'll figure out a way to get that number. But I'll tell you right now, this is going to be pretty close. For our approximation, well close enough. It's going to be about 2.4, maybe 2.5. About 2.4 times 10 to the negative 26 kilograms, approximately. I got to figure out what N is. To figure out what N is, since I know the volume, I know the temperature, I know the pressure of the gas, and I know our good friend KB, let's solve for N, and we'll put that number in here, because that'll give us the mass. And this is kilograms per particle. Yes?
You said that the average mass of air was 4.74, right, times 10 to the negative 26? And so this now is for water vapor?
Yes.
And water vapor?
That's the gas.
Okay, and water vapor is half what air is, roughly?
Approximately, because think about air being approximately 2 oxygens, a little less than the mass of 2 oxygens. Well, water has 1 oxygen, and hydrogens are really, really small by comparison.
Yeah, okay.
So it's a little, give or take about half. Okay?
Okay.
So again, when in doubt, if you can keep things in perspective in your head, God, it makes life a lot easier than guessing with equations. And always look things up. I would never give you an exam without giving you a way to get that information. But just the more you can gain perspective, the better. I just made this problem up in class, by the
pretty
way.
much the same as oxygen?
What's that?
Is nitrogen about the same atomic
Yeah,
weight?
nitrogen's about maybe 10% smaller
Okay,
in its N2 form.
okay.
It's the difference between 28 and 32. A little more than 10%. So again, we're close enough for this problem. This is engineering work now. We're making some very basic assumptions. So to get N, I'm going to use the ideal gas law. And what I'm going to do then, to apply it, I'm going to solve for N gas. And it's going to be equal to the pressure of the gas, which we've already calculated, the volume of the gas, I can't remember if we calculated that, divided by the temperature, which we will assume is 100, because the water's at 100 as it's boiling off, and the only heat coming in is the heat required to boil off that water. The surface of the water is 100, so there's no reason for it to get any hotter other than the pressure changes that affect the critical temperature, and we're not going to worry about that because there's not enough to matter here. Okay? Times the Boltzmann constant. This will tell us numerically how much do we have. Well, the volume of the gas, or the pressure of the gas, is about 1.13 times 10 to the 5th Pascal, or newtons per cube per square meter. The volume of the gas, now I have to make another assumption here. This volume here is easy to calculate. You take the surface area and multiply it by 0.05. This little difference will be the difference because of the loss of water. So now there's more space for gas to. Turns out that's going to be tiny. I mean, I just did a quick, fast estimate, and it turns out to be almost nothing. So it is pretty small. But let's assume that the water changes by, we said 15%, so why don't we use that? So what was the initial volume of the water? What was V naught? Did we calculate that at any point?
I
So
think we did.
V naught, we said was, well, it's surface area times L naught. It's A cap times L naught. And that should be about
Well, that was the
0.032 times 0.0134 meters squared. So
it's about 1/1000.
of a cubic meter?
Yeah.
Okay, it's about 1/10 of a liter. Well, I mean, it's not insignificant, but it's pretty small. So it's about 0.0001 meter cubed. Okay? Now, how much of that, how much lower is it? Even though the number wasn't quite right, we assumed it was about 15% water loss, because that's approximately how much went into the gas state. So we're talking about 1/10 to 1/15 of this, or 10% to 15% of this. Okay? That's this little water difference here, because we have to add that to this value. Does that make sense? Okay.
But that,
So the volume of water loss is about 15, give or take, and again, this was an estimate. About 0.15, 15%, give or take. I know it's not going to be 15% because my estimate makes it much lower. It's gonna be about this times this number. Give or take.
I think it's zero.
It should be, it's 1,000, not 10,000. That would be a cube.
So this would be 1,000? Oh, one, okay, I'm sorry. Here we go. What's that?
In the diagram.
Oh. So this is going to be about 1.5, I'm gonna move this decimal point over, times 10 to the fourth, negative fourth. This volume then is gonna be about A cap times 0.015 plus this. So the volume of the gas is going to be equal to the volume of the water loss, call it delta V water, plus A cap times this delta L, if you will. This is probably going to be negligible, but I'll keep it for now just because. So we have, again, 0.0314 times 0.05 now. 0.015 or so? Or 0.045? Or 0.045? 0.045. Plus 0.00015. This is pretty small compared to that.
That's the final product.
Is that right? Am I off?
Kind of went ahead.
I've got a 0.0015 for the one your hand's under.
For this one?
Yeah.
Did I? Okay, so 0.03 times 5, 0.15. Yes. Absolutely.
Yeah.
About 1.7 or 0.0017?
No, 1.6. It's
Once.
just rounding.
The next digit after the 5 there.
Yeah,
Oh,
being
this is a
1.7.
six?
Yeah.
So this is about a 7 to an 8. Okay. That's the volume of the gas. I know it's a lot of work, but you have to figure these things out sometimes. So what then is the number of gas particles? We take our original gas pressure, we multiply it by that crazy little number, 0.0017 meters cubed, and we divide all of that by the temperature of the gas in Kelvin. So 373 Kelvin, and then we multiply that by Boltzmann's constant. And that'll give us the number of gas particles. Fifth, so fourth, third, second. So 1.7 times 10 to the second power. It's going to be a pretty good size number. Tell me what that number is. Four times 10 to the 20th, maybe? Times 10 to the second. Third, second, first, negative 0.1, negative 19, or 19. So 4 times 10 to the 20th?
22.
22. 4? Something?
3.4.
Okay.
That's what I got. Check it.
Okay, double check that number. That sounds, it's going to be 10 to the 21, 29, somewhere in that range. So I'll go with it. Sounds reasonable. Very reasonable. So that's how many gas particles. So we would put that number in here. So how much mass was lost of water or evaporated? 8.
0.0008.
About that? About 3 kilograms or 8 kilograms? Or 8 grams, which is about 8%. I said 15, this is about 8%. It was off a little bit to evaporate that much. Right? Remember we said, I assumed it was 15% of the water. 1 kilogram, we lose 15%, that'd be about 15 grams. We didn't do the calculation, but give or take about 15 grams. Well, we're half of that, so I was off. But this is how much mass undergoes phase change. So how does that affect the overall energy absorbed to lift this little platform? It changes this number by about a factor of 2. It drops it by about a factor of 2, right? Yeah. So this becomes, give or take, about 1.8 or 1. No, it's not 1.8. 1.6. So you lose about 15,000. So this is somewhere around 5. Does that sound about right? I'm just assuming I lost half as much water than I thought I did, which means this number would be half, because I would have only evaporated half of it rather than all of it. These numbers don't change because this is the lift, and this was the temperature change of the water to get it there in order to evaporate it. So this number's off, was off by a little bit. So I was way off with my number by 20% or so, but that would be how much energy would be required to do this. This is the work to lift the platform, this tiny little bit. So tomorrow your lab, I think, is going to be a gas law lab. So you'll get a more opportunity to look at this ideal gas law. Where we are then, with all of this now, is going to be using gas relationships because they're the easiest to deal with. Every liquid is slightly different. Matter, solids are slightly different depending on their crystal structure. Beauty of gases is as long as they're relatively cool or relatively warm and relatively dilute, not real dense, that's always the case. Within 99%, this expression is always right. So we'll be able to use it and take advantage of it. So everything from here on out is going to be looking at the thermal heat transfer consequences of what happens to a gas when you alter it by giving it heat. And how does that result in mechanical work? So there's some cool stuff to do. But that's where we are right now. Cool beans, guys. Have a good afternoon. And again, I will be around today. I know you get enough physics for one day, but I will be around if you want to talk more about it. You really got to think about it. It's pretty easy, but then when you start thinking about it, you really got to think about where things are changing. And I made one big assumption, which may have had a small effect on this answer. Can you think about what that might be? What was my first assumption of volume? I lost 15% of the water, and I used that to calculate the volume. If I didn't really lose 15, based on just using that number, I get 8%, just half of that. Now, if I used 8 and did the calculation again, I'd get even closer. The chances are I probably lost 6 to 9% of the total water, 6 or 9 grams of water. So that's not 8%, that's 0.8%.
Right.
Oh, correct me on this. I'm full of shit sometimes. In other words, that volume is almost negligible. we could redo that calculation without even worrying about the volume change for the water, and probably be closer than using 15%. I overestimated the volume, which means I'm going to slightly overestimate by the same fraction the number of gas particles, which means I'm going to overestimate the amount of heat needed. So if this number is less than or 1% or less, that's going to make that number even smaller. It also means that this number changed significantly. It's more like 1.6 times 10 to the 4th, which means this number's tinier. Okay? When you see this, correct me. I don't mind being wrong, because I'm just doing it in my head anyway. So it's good that you check, because then you're piecing it through. Okay? And I don't mind. That, track at home, that would be that. Now we'd be left with 3. That's negligible.
0.4.
About 3.3, maybe 3.2, often almost half. Or, that sounds about right.
But I'm trying to understand your,